With some clever node placement, it's easy to get some really cool effects using Blender's shader system. So I looked around and I realized that no one has made a video on this yet, maybe for a good reason. I realized that something like this might not get a lot of views, but I just decided someone had to do it. So I decided to take one for the team real quick and present to you all of the Blender material nodes explained as quickly as possible. I wanted to specifically make this a resource that clarifies some of what the documentation says. So with that, please enjoy this resource. It took a stupid amount of time to make. Enjoy, everybody. The ambient occlusion node takes whatever ambient occlusion is being generated on the model and returns it either as color or black and white data. That means in cycles it should be working automatically, but in Eevee you're going to need to check the ambient occlusion box in the render properties settings for it to start. Samples control the resolution, inside basically treats it as if the model is inside out, only local means other objects won't affect the ambient occlusion, color gives it a tint, distance controls how far away other objects can be to be considered for occlusion, and the normal input allows you to use a normal map that will also be included in the ambient occlusion. The attribute node is a testing node that allows developers to use attributes of models that they haven't created a node for yet. Most of these attributes actually do have nodes now, but you can use it to input things such as normals, vertex colors, and UV maps just by typing in the name and output that as a color, vector, or black and white data. The camera data node returns data based on the camera, as you might expect. The view vector node shows you data based on the model relative to the camera's position. The view z depth displays a linear gradient based on how far away the camera is from that part of the object, and the view distance does the same thing except with a radial gradient instead. Fresnel is an algorithm that determines where light should be reflected and where it should be refracted off of an object. In my experience, it's most commonly used to mix two materials, and it can be used to great effect, as you can see here. Next is the geometry node. This one is a beast. The first output gives you the actual position of an object. The normal output will give you the normals of the object in world space, not local space. That's the difference. True normal is just like the normal output, except if your object is flat, it's still going to show that even if you've shaded your model smoothly. So back facing returns black for the backside of a face and white for the inside. Hair info does exactly what you might expect. It can tell you whether something is a strand, where the ray intercepts with the strand, the thickness of the strand, and even return a random value to maybe randomize the hair color and things like that. The layer weight node is similar to the Fresnel node, except it has a few more options. To start, we also have this facing output that is similar to Fresnel, except it has a more linear fall off. Additionally, it's much easier to work with when you're using a 0 to 1 scale instead of the alternative. If you're into tricking the renderer, the light path node is for you. Starting with the is camera ray, this will show you if what you're looking at is a direct view of the camera or a result of a reflection from another object. And this could be useful, let's say you wanted to remove extra detail from the reflections in your scene to save you some render time. Well, that's what you would use. Shadow ray does something similar for shadows, diffuse does something similar for diffuse, glossy. This one is singular ray, actually has to do with how sharp the glossy will be. Reflection is pretty much what you would expect. In this case, it's actually going to be the exact opposite of the is camera ray. It will show you when something is the result of a reflection or if it's a direct view of the camera. Is transmission ray does the same thing with transmission. The ray length returns data based on how far light travels between each bounce, so if I pair that with a transmission, you'll see that it becomes darker the shorter the light bounce is. The ray depth gives you access to how many bounces a light ray currently has. This could be useful for things like optimizing glass, and the other depth outputs do the same thing, return the number of bounces with various different types of shading. Object info node. Location, as you might expect, tells you the location of the object, randomize UVs and things like that to avoid repetition. Color gives you the object's color. Object index gives you the pass index in the object panel. Material index gives you the material pass index down in the settings of the material. And random is probably the most fun because it'll give you a random value for each object, meaning you can give it random colors and things like that. Particle info. So the particles are numbered and the index gives you the number of the particle. The random output will give you a random per particle value. Age shows you how many frames the particle has been alive. Lifetime gives you the number of frames it will be alive. Location gives you a vector of where the particle is in space. Size gives you the size of the particle. The RGB node is pretty simple. It just returns a color value that you choose with this color wheel. The tangent node is great for creating a custom tangent for an anisotropic BSDF. Further customization can be made in the anisotropic BSDF, such as rotation and the amount and color. But with the tangent node, you can control how it's projected onto the surface, such as with a normal cylindrical projection, or you can actually use a UV map. The texture coordinate node helps you define where a texture should be placed on an object. The generated output is used when maybe you don't have UVs set up and you want something to be done quickly based on the size and shape of the object. The normal output can be used to determine which side of the object you're looking at. If you run it through a separate XYZ node, you'll be able to control it, say from the side, the top, or the other side. You could use this to swap between two different materials and say add snow to the top of your objects or things like that, or dust. But do remember that this is local space, not world space, so it's not going to change if you orbit it around. The UV output will control the texture based on the UV map you've created for the object. The object output is very interesting to me because you can use this eyedropper here to select something that you have in your scene, and then you can control the texture based on the rotation, the scale, and the position of that object that you chose. The window output is similar, except it uses the entire window and not just the camera. I really like this one, and I feel like there's definitely something to be made with this. The reflection output UV map lets you output the UVs of any map that you choose. It's especially useful if you have multiple UV maps on one object. Value node outputs just a value. As far as I can tell, it can be basically any value. The wireframe node gives you the wireframe of an object and allows you to control the size of how it appears on that object. Since we're working with material nodes, there's only one output node that we need to care about, and that is the material output. Essentially, this is the end product of all of the other nodes that you have in your setup. You can, of course, attach something into the surface output and use some sort of surface shader to control the way it looks. Alternatively, you can use a volume shader, which we'll get to later, and place that into the volume input. The displacement input is for when you want to use some bump or normal data. Now that we've got that out of the way, let's talk about all of the different shader nodes. The first is add shader. Essentially, it's going to just add any shader data on top of any other shader data. For example, if you add a diffuse and a glossy together, you could get a nice porcelain or ceramic material. We've talked about the anisotropic BSDF before when we talked about the tangent input. I think the best way to think about what this shader does is to think of the bottom of a kitchen pan. It's one of the only places I've seen this kind of effect going on, but it's a great way to bend the light around a certain point. Now, this is the diffuse BSDF. This used to be the default shader for Blender materials. And so now I think it's a good time to discuss what exactly a BSDF is. It's called a bidirectional scattering distribution function, and essentially what it's meant to do is calculate how light rays should interact with the surface. The diffuse BSDF does it much differently than something like a principled BSDF. This is now the default for Blender, but we'll get into that a little later. In the diffuse BSDF, we have a color input, a roughness input, and a normal input. The color, as you might expect, adjusts the color of the surface. The roughness adjusts how precisely light rays should be reflected off of the surface, and the normal input allows you to use something like a normal map. For most practical uses, the emission shader turns any surface into an emissive surface. You can use a color input to change the color or maybe make it some sort of texture, or you can use the strength to adjust how strong the emitted light should be. The glass shader also works how you might expect, turning your object into glass. The first parameter is the distribution function. These are the same options that you have with the glossy BSDF. Most users will not have to worry about these. Next, you have a roughness input, and this determines the sharpness of the refraction. Imagine it like this. If there's a sun or a light ray coming into the glass like this, with a roughness of 0, it's going to hit the surface and then bounce straight through. However, if the roughness is something like 1, it's going to hit the surface and then scatter throughout. That's kind of how you can imagine roughness. And as you can see, this is the result of all of that light scattering. The IOR is something that we call index of refraction. You see this option in a Fresnel node as well. It tells the light at what angle it should pass through. For instance, if you have an IOR of exactly 1, it will be pretty much a perfectly clear object because the rays are literally passing right through. The default is 1.45, but you can adjust this if for whatever reason you felt the need to. The hair BSDF is what most people used to use for hair simulations. You can of course adjust the color and all of that, however it has most recently been nearly replaced by the principled hair BSDF, similarly to how the diffuse BSDF is now to the principled BSDF. The holdout node is something that you don't hear talked about a lot. What if I told you that there's a Suzanne that is visible in this scene? Yeah, it's not visible. You can only see it if you turn the scene like this. That's right. What the holdout shader does is turn the object into what is essentially an alpha mask. So you could mask out other objects. You could do really whatever you want with this, and to make sure that it works, turn the film to transparent in the render properties, and that's pretty much what most people will use this for. The mix shader is used to mix two different shaders together. You've got this slider, which will determine which shader has more effect over the other. As you slide it towards the left, it will use the top shader more. As you slide it towards the right, it will use the bottom shader more. You can, of course, control this with any type of black and white data. One of my favorites is the Fresnel input node. If we plug that into a viewer, we can see exactly what that data looks like. And now you know about what IOR is, so you can change that to whatever's appropriate for your scene. The principal BSDF node is truly a gift. There are so many different options, it's almost impossible to talk about them all in detail without going far over time. As you might imagine, the base color is again the color of the surface. The subsurface has to do with subsurface scattering, which we will explain later as it has its own node actually. The metallic will adjust the metalness of the surface. Usually though, this should be 0 or 1, and you'll see if you use a metallic texture that those are usually very polar black and white. For the average user, specular means how much reflection is possible. For example, if I took the roughness all the way down but the specular is at 0, we're still not going to see any reflections. However, once I turn the specular up, now we can see all those nice reflections. Roughness works similarly to how it does literally everywhere else. If you turn it down, the surface will be less rough and provide sharper light reflections, and conversely, when you turn it up, it will scatter more light, reducing the sharpness of the reflections. We've talked about anisotropic already. Sheen is used mostly for cloth-like materials, and it has to do with the way that the light interacts with the edges. Clear coat is going to add a nice glossy specular layer on top of everything else, and this is really useful if you're making anything that has to do with paint, specifically car paint or boat paint. Here again we have the index of refraction as well as a transmission slider that can turn your material into a glass-like object. We also have an emission input to turn your object into an emissive surface. I personally like to use the emission node over this emission input simply because I have more control over the strength of the emission in a more convenient way. With the alpha slider you can adjust the transparency of the object. And now we have the normal input, which you can use normal maps with, clear coat normal, which will adjust the normals of the clear coat, and then of course the tangent if you're working with the anisotropic. Here you can see some nice images that describe the way some of these settings work. You can find these images in the Blender documentation. The principled hair BSDF is pretty much what everyone uses for hair nowadays. As you can see on a basic hair particle system from a plane, you can see it looks incredible. Here we have the color parametrization. And you have three options here: direct coloring, melanin concentration, and absorption coefficient. And the direct coloring is probably the easiest for most people. You can pick pretty much any color, and it's going to try and choose the necessary absorption coefficient to make it work. If you want to take a little more technical approach to it, you can use melanin and melanin redness, and all of these melanin numbers mean something. So 0.25 melanin will be a very strong blonde color, while black hair would be a melanin level of 1. You can tint it certain colors with this, but the more melanin you have, the more difficult it will be to do this. The next one is absorption coefficient, mostly for technical users. I don't think many of you will be using this, but you can read more about it on the Blender documentation. Next is the principal volume node. You can use this for models, or you can use this for things like smoke. The refraction BSDF is used, as you might expect, for refractions, but it's not meant to be used on its own. You should be combining it with things like glossy and transparent shaders if you want to, for example, create a custom glass setup. This next one is subsurface scattering. Essentially, light doesn't go straight through or bounce straight off. It will bounce around internally before leaving. It's useful for things like wax or skin or marble. The Toon BSDF is used to create cartoon light effects. Keep in mind that this is not what you're looking for if you're looking to create some sort of cel-shaded effect. Translucent BSDF, for most users, simply increases the ability to see through some of your objects. The transparent BSDF, on the other hand, allows you to see through them entirely. The Velvet BSDF is used for fabric-based reflections. However, it's not very useful on its own. You'll want to combine it with other shaders. Volume absorption and volume scatter are different types of volume shaders. Let's talk about the different texture nodes. First, we have the brick texture. This is a fun one. You can adjust the size of the mortar in between the bricks and the size of the bricks themselves. You can of course adjust the color of all of this, and with all of these parameters, you can make some pretty cool brick-shaped textures. Next up is the checker texture. You can adjust the scale and the colors with this one. Next up is the environment texture. For some reason, it's available in the shader textures, but I've never ever seen this one used except in a world output. It's what you'll use to introduce an HDRI or something everything like that. Next up is a gradient texture. You've got all these different types of gradients to use. I tend to use this one with a converter map node, and if you play with the value in here, you can adjust the position of the gradient pretty easily, and you can even add in another one and make it and turn it to multiply, and then you can adjust the fall off pretty easily as well. An IES texture is a special kind of texture that uses a special type of file type that I've never even used before, but it's a special data type used to mimic real-world lights. If you happen to have an IES texture, you would switch this to external and then find that texture wherever it is. Now the next one is the ever popular image texture. Image textures can be mapped onto surfaces, and I cannot stress how useful they are. If you want to instead use a video texture, make sure that you change this parameter from single image to movie, and then you've got to choose how many frames you want it to play, which frame it should start on. If you want the movie to repeat itself, you can just choose cyclic, and make sure you check auto refresh to be able to preview it. Now the next one to care about is color space. If you're working with image textures and you happen to be using a roughness map, a specular map, a metallic map, and all sorts of maps, the base color and if you have an ambient occlusion texture are the only ones that you should have the color space set to sRGB. Otherwise, you'll need to make sure to set it to non-color, because that will tell the engine that you're not actually just trying to output color data, it's being used for something else, because otherwise you can get some really weird results, especially with the normal maps. So make sure to change that. For the magic texture, I was going to make a clever joke, but I think I'm just going to play with some settings and just let you figure it out. I've always seen the Musgrave texture as a bit of a glorified noise texture. Here you can see some examples of what you're able to pull off using a Musgrave texture. There's 5 different noise types here. It's got some pretty incredible variety. The noise texture, however, is an easier noise texture. There's 3 main things to worry about. That is scale, detail, and distortion. And the good news is those all do pretty much exactly what you would expect them to. Sky texture is again one of those things that is mostly only used for world outputs, so you probably don't need to worry about it when you see it in the node menus. The Voronoi texture has a specific noise pattern that a lot of people remember it for. However, it's possible to generate a lot of different ones, as you can see in these diagrams. Here's some really cool uses of the Voronoi texture. Next up is the wave texture. I use either bands or rings based on whether I'm using a curved object. You of course have the option to adjust the scale, the distortion, that's a cool one, and the detail scale. The white noise texture only returns a single value based on any kind of vector input. You know, it reminds me a lot of the white noise that you might see on a blank channel or something like that. Starting us off with the color nodes is the brightness and contrast node. Now this pretty much does exactly what you might think it does. The brightness slider will adjust the brightness of the color data you're feeding it, and the contrast data will increase or decrease the contrast. This is useful both in textures and in compositing, or pretty much anything else that involves color data. Now, next up is the gamma node. And if you've messed around with this before, you've probably noticed that it also has to do with the luminance. One good way to think about it is an exponential version of brightness. Now, next up we have the HSV node that stands for hue, saturation, and value. All of these values have the same meaning as they would in any color correction workflow. The hue adjusting the color or hue of the image, the saturation having to do with the potency of that color, and the value having to do with the brightness of that texture. This factor slider adjusts how effective your changes will be on the output, and that's really all there is to know about it. The invert node is made to, well, invert any color or black and white data. The mix RGB node, which can be found under color, is useful for combining multiple different images or textures. For instance, here I've overlaid a noise texture over a brick texture. As you can see, there are multiple different blending modes that are available. The ones that I use most often are mix, which literally just blends the two together, and you can use the factor slider to adjust which has more control. You can see a lot of the technical definitions of these blend modes by going to the GIMP documentation. I will link this in the description for you. The light fall off node is a bit tricky to describe. I've only seen it used with lamps. Now I know this isn't a material necessarily, but it's pretty cool. So essentially the light fall off will give you the light fall off data here. If you try to put a gradient or something and attach it to the emission of a light, it's not really going to do anything at first. But if you use the light fall off data, and you may need to do some manipulation with the data, we'll get to these converter nodes in a bit, but let's say you use the multiply node, and you're going to need to bring it down to a value of 0.2, throw in the linear light fall off data in there. These are the different ways that light is calculated in cycles, and this only works in cycles, by the way. I'm going to bring the strength down to 1, and then bring the multiply value into the color ramp. And well, here you can see you can make really cool customized stylized light effects. And finally, we have RGB curves for color correction. You do of course have access to the RGB channels, as well as the ability to reset the curve under this arrow menu. Moving on to the vector nodes, we're starting out with the bump node. Now essentially what the bump node will do is create a modified normal output based on the input of a height map. Now you can use really anything here. I'm just using a black and white output from a brick texture mapped based on the camera. The strength is pretty self-explanatory, but the distance can be thought of as sort of a multiplier. Now the vector curves node works very similarly to the RGB curves node, except with vector data. Now I haven't seen this used very often in materials. In fact, it's most often used in the compositor when working with the vector blur effect, which can be used as a faster, less expensive motion blur. But you can use these curves to adjust the angle of such an effect and some other things. There are 3 curves in here. There's the X, the Y, and the Z, and you can manipulate them all by clicking and dragging to create new points on the curve, as well as using this arrow drop-down menu if you would like to do something such as reset the curve. Now for the displacement node, I wanted to bring you to a material that I worked on a while ago. Now this node setup was not very well organized necessarily, but I think it's a fun example for how the displacement works. So essentially what the displacement will do is take a height map and displace the surface of an object along the normals of that object for more detail. As you can see, unlike a bump map here, the outline of this object, the silhouette, is actually detailed. This is real geometry that's going on here. And that is because this is a very finely subdivided model. You need a lot of geometry to be able to have something like this work. I have a subdivision surface modifier on here that is resulting in over 63,000 vertices, and it's not even a whole sphere, it's just a half of one. So should you use this displacement? Maybe. If you're doing a lot of close-ups and you really need that fine detail, this could be worth it, especially in organic-based materials. This looks incredible. But if you're planning on using this in other places, you'll definitely want to simplify the geometry. Now, finally, let's talk about this mapping node. As you can see, we've got a location, a rotation, and a scale input in here. Now, these all can be controlled by other vectors, or you can adjust the values manually. For example, with the location, we can adjust the position of the texture on the model. With the rotation, we can do something similar with the rotation, and as you might expect, the scale will adjust the scale on the object. Converter nodes do exactly what the name would suggest, converting one type of thing into another. Let's start with the blackbody node. Now, this essentially can convert a temperature into a color output. Here you can see some examples of the colors that are emitted based on their natural frequencies. Next up, we have the clamp node. I'm using a Voronoi texture to illustrate this. Black and white values tend to go from 0 to 1, 0 being entirely black and 1 being entirely white. Now with the clamp node, you can set minimum and maximum values for these things. So if I believe that the darks are much too dark, I can set a minimum dark level and it will clamp out some of those darker areas. Same with the maximum. If some areas are too bright, all I need to do is decrease the maximum and it will gray out all of those light areas. Next up is the color ramp node, and if I had to pick a favorite node out of every single node there is, it would probably be this one. It's just such a versatile node. It's just incredible. So there's many uses for it. One of them is colorizing images. You can use a color wheel to select a color and use that as a substitute for whatever you're inputting. So in this case, it's taking the black and white and essentially just replacing black values with red values. I can do the same with the white side. I could turn that to blue. Really, there's infinite possibilities here. One of my favorite things about the color ramp node is that you can change the interpolation from ease to cardinal to linear to B-spline, and one of my favorites, constant. This means the data will have no fall off at all, and you can generate some insanely cool effects with this, especially if you're trying to work with cell shading or something like that. Next up, we've got the separate and combine nodes. Now, the first of these sets are the separate and combine RGB. Now, essentially what this will do is take color data and separate it into the red, green, and blue channels, and then the combine RGB node will combine all of them together and then output the color. So why would this be useful? Well, it pretty much allows you to adjust the individual channels, and that could be really useful for a variety of reasons. Next up, we have the separate XYZ, which will turn a vector input into its separate X, Y, and Z values. We already talked about how those are significant. And then, of course, the combine XYZ will take all of those and then output another vector. And then finally, the separate HSV. Yes, this is hue saturation value that you are separating. If you'd like to adjust any of those parameters individually, it's all up to you. You can think of the map range as kind of readjusting the minimum and maximum. So if I input this Voronoi texture here, which tends to output, as we said before, values from 0 to 1, here we can readjust it. I mean, you could make the minimum -1 and the maximum 2 if you wanted. Now, this is especially useful when what you want to output is not within the range of 0 or 1, such as particle age or things like that. Next up, we have probably the most intricate individual node, and that is the math node. And it's probably the most complicated because, well, you have all of these parameters down here, but the main one is this box. And if you open that, you can see that you have so many operations that are ready to use here. They're all mathematical and used for conversion of values. Now, I've had to use add, multiply, less than, greater than, and maybe a couple of others from time to time, but the average user may not find the need to use this very often. So I'll provide you with a link to the Blender documentation, which in turn has links to approved resources on each of these functions. Next up, we have the RGB to black and white node, and that does exactly what you think it does. It takes in a color input and then outputs it as black and white. Now, I almost didn't include this one because it's Eevee exclusive, but it's shader to RGB. And it's actually pretty cool what it does. And essentially what it does is it takes shader data and turns it into RGB data. And that includes the lighting, which is awesome. And so with that, you can actually take it and run it through a color ramp node, for example. And then what did I tell you earlier about the constant? And now you can do things like really nice cell shading and whatever other creative effects you come up with this. Next, we have the vector math node, and it's essentially just like the math node, except instead of working with single values, you're working with sets of 3 values or vectors. Now, there's not as many operations here, but the description of each of these is on the Blender documentation, so again, I'll link that in the description. And finally, for converters, the wavelength node is used to create a color out of a simple wavelength number. I imagine this makes it pretty easy to animate so you can finally have your RGB gaming cube. And finally, we have everything that I would consider miscellaneous. The first of which is the script node, and this is simply used to grab Python scripts. The make group option under group is for when you find something that's particularly groundbreaking. You just go to group and choose make group to create group inputs and outputs. You can rename these group inputs by pressing the N key, and then you can set those up to go where they need to be. And then once you're ready and you've figured it all out, then you press this arrow key. Now you've got your custom node all ready to use. It outputs as a shader in this case. And if you need to add it again, you can go under group and choose which group you want. Really nifty for organization. Speaking of organization, we've got layout nodes. The first one is a frame, and that's really useful for organization, as you can see here. If you want to call it something other than frame, make sure to just type in the label box something other than frame. And since we were speaking of organization, we've got this. Essentially what this thing will do is create a subdivision in the node connection. You right click to drag it around, and now you can reroute your node noodles all over the place. And well guys, that does it for the explanation of all of the nodes.
Today I will show you the most of the nodes from the subcategory geometry in the system geometry nodes in Blender. Now we are here in Blender and we can leave the cube. We can delete everything else. With that, we can go into the geometry nodes editor and we can create a new node tree. So in geometry nodes, you can manipulate the geometry of your object via several nodes. Here we have an empty geometry nodes tree. So the geometry will flow in. Then it goes through our node tree and then it will go out, and everything that goes out of here will get displayed here in the viewport. And so we can manipulate the geometry here in the middle, and we can do that with nodes. But how can we add nodes? We can add nodes here on the top left by clicking the add, and here are a bunch of nodes. But we also have a shortcut for this. It is Shift and A. You can press that, and today this video should be about the geometry submenu of this whole add menu. And the first node we see is the bounding box. We can click that, and to have it function we have to drag it over our noodle, and we can see our noodle turns white, and then we can release our mouse and it will already be connected in the middle here. And we can see also nothing changed, And this is because we have already a cube, and this node does nothing else than just taking a box and wrapping it as near as possible on our mesh. How can we see that? We can go into X-ray mode and into wireframe, and then we can take our original face here on the top and we can scale it down, and we can see Geometry Nodes puts this bounding box around here, and we can even manipulate our mesh. For instance, if we extrude this here, we can see Geometry Nodes takes a box and puts it as best as possible around our mesh. And we can do even more. That doesn't affect anything, like this. And this is the bounding box. It's a pretty simple node. The next is the convex hull, and this is a similar node but more complex. This looks first of all like this. This is like if you are using a plastic bag and sucking all of the air out of it, and then our object then looks like this. And we can, of course, more manipulate our mesh here, and it also works for vertices. So if we will go into the vertice mode here and we will duplicate a vertex, we can drag it out here, and with that we can define how our convex hull looks. A nice effect for this is if you are using, for instance, a volume, like if we will use a volume cube, and we will distribute points in it, distribute points in volume, then you can see we're getting interesting structures here, and with that you can create nice bricks like this. And the more points you have, the more defined is the object, and with that you can create really nice effects. And the next node is the delete geometry node. And this node just explains it from its name. This node deletes your geometry if you put it like this. But if you define a selection, so a mask, it will only delete the parts of your mesh where your selection takes effect. For example, if we will subdivide our mesh, so we have enough geometry a bunch of times, and for the selection we will take a noise texture and we plug the factor into the selection. First of all, nothing happens, and this is because our noise texture does nearly happen to go to a value of 1. So we need to have a color ramp to crank up the contrast and set it to constant. And now with this, we can define here the clamping. With more resolution and a lower scale, you can have also effects with this. And yeah, this node is for deleting parts of your mesh or whole objects, or just deleting geometry, as the name says. Let's delete everything again, and let's go over to the next node, which is the duplicate elements node. And this is a really nice node because we can duplicate things from our mesh, and then with the help of the duplicate index we can move every single duplicate somewhere else. So we want to duplicate our faces, but now you say, yes, we can duplicate this, but nothing changes. So if you duplicate it twice, I don't see it 2 times, and this because it gets overlapped. And so we have to move our mesh, and for this we will already use the set position node. So the set position, we will always use the set position node if we want to move something. For this we want to have a combine XYZ node, and we want to have the duplicate index for the Z axis. And now we can see if we higher up the amount, we will get more of these objects or less. And the duplicate index just outputs us at the first duplication a value of 0. So it gets moved up by an amount of 0 additional. And then the first duplicate has a value of 1. So it gets 1 unit on top, and so on and so forth. And this is the duplicate elements node. And you can also limit it to vertices and everything you want to have. So the next node is the geometry proximity node. This is also a very cool node, probably the coolest node in here. Drag it here outside of the noodle. And I want to not use our object here. I want to use a plane. And for this, I go into the mesh primitives and use a grid. Of course, I want to have it scaled up a little bit so you guys can see what I'm doing. And now I want to have also here now on the viewport, I want to have an additional object, a sphere, an icosphere, and I'll drag it here on the side. And now I want to have the effect so that around the icosphere, the ground should rise up a little bit. And how can I do this? I first of all need the information from our icosphere in our geometry nodes tree. So I drag the icosphere over to my geometry nodes editor and I release. And now I have the object info. Don't forget to set it to relative so it takes the current position and not the original position. Now I want to have the distance from our icosphere to the geometry of my mesh, so the grid. And so I need the proximity of my icosphere. And now I have here outputted the distance, and I can use it again with the set position node. And by combining the XYZ, I can only use the Z-axis, and now you can see something's happening. But let's higher up the amount, and let's also use a color ramp to define better the contrast like this. And let's reverse the whole thing like this. And now you can see if I'll move this here, you can see it reacts to the distance of my object. So let's connect again our original mesh. Let's go back into the menu. And the next thing is the geometry to instance. And this will be used together with the instance on points node. And this node just converts your geometry to an instance. And an instance is way faster. And an instance is way faster than geometry. So we can take, for instance, a mesh primitive, a cone. And we can drag it directly into the instance. And we can check here on the timing. It takes 0.11 milliseconds. And if we will use the geometry to instance, it takes under 0.1 milliseconds. So this just makes the geometry to an instance, which is then way faster. So the next node is the join geometry. And this is a very fundamental node, because this just joins several measures, several geometries together. So you can join it here also with, for instance, a cube that is now here. And you can join it with an UV sphere, for instance. And we can transform the UV sphere so it gets up. This node joins everything together. And it has endless sockets here to join everything. The next node is the merge by distance node. And this node is self-explanatory. This node merges every vertex, every face, whatever you select here. It merges this together by a given distance. So if two vertices are under the given distance, they will get merged to one single vertice. And if I drag this up here, you can see those two vertices here are closer together, those two here. So they will get merged first. And this way you can merge your objects by a given distance. It's a little bit small up here. Sorry. And the next node is the raycast node. And this is a very interesting node. And for this we can, so here in the viewport, we want to create another plane. And we want to drag it above our object and scale it up. And now on our plane, let's create a new geometry nodes tree. And we want to have the information from our original mesh. So we grab our original default cube. This was once the default cube. And set it to relative. And we want to have the information from our raycast node. So let's just grab it here, connect it like that. And now we want to have a set position node because we want to change the position of our plane. And don't forget to subdivide the mesh a bunch of times. This node just sends rays down from our plane, and those rays contain several informations. They contain if something was hit, the hit position, the hit normal, how long the ray took to travel, and the attribute it hit. We want to connect the hit position to our offset, and this way we can see the position from our object gets transferred to our plane, and we can also change the plane position, and we can see how it affects. So let's move on with the next nodes, which are the sample index and the sample nearest nodes. Those are a little bit together because they were originally the transfer attribute node, which was located in the attribute submenu, but now they are split and they are in the geometry submenu. So for this, I want to have the Suzanne monkey, and we want to have a new geometry node tree. Now I want to have also a mesh primitives cube, and now I want to swap between those two meshes and merge them a little bit. How can I do this? I can pull the cube positions, and for this we will be needing in the geometry submenu the sample index node, and with this node we can grab an attribute from our cube and we can put it onto our Susan monkey. And for this we want to have the input position of our cube vertices. And don't forget to set this to a vector. And we want to have this into the value. And the geometry should of course be the cube. And now to change the position of our monkey, we want to use the set position node. And at first, let's plug the sample index into the offset. And now we can see it shifted. And let's look where it shifted. Join geometry. Let's join our cube back in. Our cube. Like this. And we can see, let us just scale down our monkey a little bit. This monkey is now here at the bottom. Why is it at the bottom? So if we will look here at the sample index node, this node does now take the position from our cube from the index 0. And the point of the index 0 is here at the bottom. So here we get now outputted the position from our cube for the index 0, or the vertice that has the index 0, and that is here on the bottom. The index 1 would then be here, and so on and so forth. But we now want to have every vertex on this mesh mapped to our monkey. How can we do this? We can say, okay, first of all, let's delete our transform node here, and let's plug this into the position, and we want to mix it with the original position like this, and don't forget to set it to vector. And we want to have the original position here also, so we can mix between those. Now we don't want to have one index, we want to have all indexes of our cube in the near of our monkey. How can we do this? We can do this with the second node, geometry submenu, the sample nearest. We can now plug this in between here and take the cube. And now we will be sampling the nearest points that are on our monkey. So let's look here. So for instance, this point here will now affect maybe those points because it is nearer on those points than this point. This will affect this region. And this is what this node does. So it looks, so this point is the most closest to those points, and this point is the most closest to this points on our monkey. And now we can use this into our index, and now we can see we are now using every point of our monkey and turning it into the position of our cube. And this is what those two nodes do. Let's move on with the separate components node, and this just separates the type of objects you have. So if you have, for instance, if you have joined distribute points on your faces and you've joined them together like this, you have points and you have your original mesh, and you can separate those two components afterwards by the mesh and by the point cloud. And if you have more types, you can also separate them, so curve, volume, and instances. And this is just a simple and very basic node. And the next node is also separate geometry. So here you can use a mask to define how you want to split your object. So for this, we can again use a noise texture as a mask. And we can use the factor into the selection. And let's use a color ramp set to constant. And let's subdivide our mesh so we can actually see what's going on. So let's give it some resolution here. Now we can see we have the first separation of our object, and then we have the second separation, which is the inverted one. And if we join those two together, it should give us the original mesh when you set it to faces. The next node is the transform node, which is very, very simple. With this node, you can move your object on the X, Y, and Z location. You can rotate your object in every single axis. And of course, you can also scale your object however you want to. I think this node doesn't need more explanation because the next node is the set ID node. So this node apparently is a node that you'll never be using. This just fills the ID attribute on the input geometry. You will never use it. So let's move on to the last, which is the set position node. And we've already covered this. So let's do one more example. So let's use a grid again, and let's subdivide it 100 times each. And let's use a combine XYZ node as the offset. And we want to use a noise texture for the Z. And if we will scale this up, you can see what's going on here. We have a displacement. We have a displacement here. And we can also define the contrast with a color ramp like this, and you can set it to east. And with that you can make nice effects like some crazy mountains like this. And yeah, and here we can delete everything, and we want to have our cube back, of course, as always. And now let's open up our beautiful geometry nodes editor, and we want to create a new node tree. In the last episode, we looked at the geometry nodes. Funny, we looked at the geometry nodes in geometry nodes. All those nodes, you can watch them if you haven't watched the episode before. And today we want to look at the mesh nodes. First of all, adding nodes with Shift and A. So, and we will be starting right now. So the first node is the dual mesh node. And if you use this node, it seems quite confusing, but just what it does, it takes every face and puts for every face a vertice. So a vertice here, and a vertice here, and a vertice here. So just for every face. And then what it does, it connects all of those vertices and creates a new mesh. And what do we got? Exactly this. So with this node, you can also create really cool effects. For instance, if you take with Shift A into the add menu, if you take a mesh primitive, an icosphere. So if we look at our icosphere, first of all, I will erase my annotations. We can see that we have here, so for every face, I will draw our things here like this. And we can see that we get those kind of shapes. And with this, we can make really cool shield effects. So if we take the dual mesh, you can see that we get really cool effects. And of course, you can subdivide it and you can create shields with that. So let's move on to the next node, but maybe we'll erase my stuff here, which is the edge paths to curves node. So of course, I can't show you this node on its own. We have to use a couple of more nodes to show you what this node does. But basically this node converts our edge paths, that converts it to a curve then. But to show you what it does, we need another node, which is also in the mesh submenu. It is the shortest path node. You can find it here. And we can plug the next vertex index in the next vertice index. So for a better example, let's delete this and let's take a plane and subdivide it a bunch of times, maybe 5 times, but simple. And here in geometry nodes, we want to use our edge paths to curves node. And we want to also use the shortest edge path node. And let's plug the next vertex index into the next vertex index. Now this node calculates the shortest path from every vertice through the edges of our mesh to our set end vertice. So we have to define an end vertice. How can we do this? We can just, maybe if we want to have this as end vertice, we can select that and we can go into the vertex group and create a new one and click on assign. Now we have to import this vertex group into geometry nodes. So let's grab our noodle here from the group input because we want to input our vertex group, and let's plug it into the end vertex. Now in our modifier properties, we want to use the end vertex and we want to use an attribute for this. And let's grab our group attribute. Now geometry nodes finds from every vertex the shortest path to this vertex. But what if we not want to have all vertices calculated to this vertex? We want to have one vertex. So let's grab another vertex, maybe here. And let's create another vertex group and let's assign this. And we want to have this as the start vertice. So let's grab that. And we want to have the other vertex group. Now geometry nodes finds the shortest path from this vertice to this vertice. But this node as default takes every edge as the same cost. We can define different costs for different edges. So we can grab a random value node and we can give every edge a random cost value. So geometry nodes goes from our start vertice. It calculates the shortest path to this, and then it looks what is the most cost efficient way to get to this vertex. And we can give every single edge another cost value, so it finds the easiest way to our vertex. So if we plug a random cost value in here, you can see it finds its way around to here. If we look at our cost values, they look like this. And we can of course change the seed. So you can see always Geometry Nodes tries to get to this point in the cost efficient way. And we can define the cost for every single vertex. Of course, we can also use a noise texture for this, for the edge cost. And here we can also change the scale. But normally for the edge cost, we use the edge length, because the longer the edge, the more cost it should have. So it should be more unlikely that Geometry Nodes finds its way through the longer edges. And we can calculate the longer edges in the mesh submenu if we use the edge vertices and we use a vector math node set to length. We can, set to distance. We can use the position 1 and position 2, and we can calculate the distance for every edge from the first vertice to the second vertice, so just the length of every edge, and we can plug that into the cost. So edges that are shorter have more weight than edges that are longer. So in edit mode, we have also, if you press down Control and left click, you can also find the shortest path. And if we now take our first vertice and we will take our second vertice and press Control and left click, we can see it's exactly the same path. So everything we did is right. So of course you can do way more with this node. This was just a very, very short explanation, but of course we want to get to more nodes, so I can show you more. So basically this node finds the shortest path in your mesh, and then it passes you the vertex index to this node, and this node then converts it to a curve. So we can also then use the next node, which is the edge path to selection node, and with this you can create a selection for every vertex that is used here. So if you grab a geometry delete node, delete geometry, and you use this selection on our plane here, and of course also the start vertice, you can delete the edge that gets used. So this is the selection for our edge paths. Moving on with all the other nodes, we have here also the extrude mesh node. And this node should be very familiar to most of you because we know what extrusion is. We can extrude our mesh here. This takes all of our vertices, all of our faces, and extrudes them. Most of you know this from edit mode. So if you take, for instance, all those faces and you press I, then you can also extrude those. And it's the same as in edit mode. So if we take all those faces and we use them in our first vertex group, we can use it also here for the selection. And then you can see we have extruded those in geometry nodes. But of course, we can also define a random value for the offset scale, and then you can get very crazy with this effect. You can also define only edges or only faces or a vertice. Do whatever you want with it. But this node also outputs you the top and the side. So if you take the extrude mesh node again, it looks very strange, but you can tell, you can say extrude only from the top. And now it extrudes from our top or only from the side. This is what those booleans are for. Enough about this. Let's move on to our next node, which is the flip faces node, and this is very simple. Our faces have always two sides. You can see them in edit mode Here you can turn on face orientation. Then you can see the outside face side and the inside side. It's very strange. But if you now take your flip faces node, you can flip them around if you need it in some corner cases. And of course you can also define a mask for the selection. And this node is very simple. So the next node is the mesh boolean. This is also a simple and cool node. You can use this to cut holes in your mesh with another object. So let's take a cylinder. Let's change it as display type as wire so we can look through it. And we now want to have everything that is in the volume of those cylinder, we want to have it cut out. So we want to have a hole in our mesh. And we can do this with the mesh boolean. So, but for that, we want to have the cylinder in our geometry node tree. So we can, via drag and drop, we can drag this into our geometry node tree. But of course we want to have it relative and as mesh 2. And now you can see we are cutting a hole in our mesh. And there are also other modes as difference and intersect. So it's the opposite of difference. So difference, you cut a hole out of the plane with the volume of our cylinder. And in intersect, we are cutting everything outside of the volume of our cylinder. Then we have the union, and this just unites our two objects together. Enough about this node, and let's move on with the next node, which is the mesh to curves node. And this one is very cool and simple. So we have here, let's delete our cylinder. We have here our grid, and this node takes every edge and converts it to a curve. With the curve, we can then make really cool animations like trim our curve like this. Let's enable the viewer. So we can make animations like this and maybe make it to 0.5. And after this, we can convert our curve to a mesh again. So we can plug in a curve primitive, a curve circle, resolution down. And let's take also our radius down. And we can then join those two together. Join geometry with our original plane. And then we have those cool patterns here. Maybe take the radius a bit up like this, so you can better see it. I'll make cavity on like this. And you can create really cool effects with that. But as said, really simple node. It just takes your mesh and converts every edge to a curve. Another node is the mesh to points node. It's even simpler one. So let's use it on an icosphere, because an icosphere is simpler. New geometry node tree. And let's use our mesh to points node. And now geometry nodes looks at every face, and it draws for every face a point. It's nothing more than this. For every face a point, and it looks like this. Now, of course, we don't have set it to a face. Of course, it also takes our vertices here. But if we set it to face, here you can see it matches my annotations. And we can also set it to edge. So for every edge, it sets a vertice, a point, and for every corner, and so on and so forth. And you can change the radius and so on. It's a really simple node. And we will move on to the next, which is the mesh to volume node. And this takes your original mesh and fills the volume and then you can make cool things with the volume. So you can remesh your model with a volume to mesh node, for example, and you can always higher up the voxel amount, and this way you can remesh your model. The next node is the sample nearest surface, and this is similar as the geometry proximity node. So we have here two UV spheres, and you can see them. We have two UV spheres, and we take the second UV sphere and set as relative, and we want to sample something from this UV sphere. Set this to vector because we want to sample the position of our UV sphere, of our second UV sphere. Now this node samples the position from this UV sphere from the nearest faces. So if we grab the set position node, we can use this position as something new. And if we now hide our second UV sphere, we can see it uses the nearest faces as the position. And you could use it to sample any kind of attribute that you have on your second UV sphere. For instance, the normal or custom set attributes, maybe as offset. That could be strange. Yes. Like this. But you can see it adds the normal to our mesh. So it works. As said, you can pull every kind of attribute that you have here on your second icosphere. So let's move on with our next node, which is the sample UV surface node. For the next node, we take a grid like this, and we will make proportional editing on, and we create something like this. We take another plane, take it on the top, and now we want to have the same displacement as here on the bottom on this plane. For this, we can use the other node, which is the sample UV surface. To have now the same position as this on the bottom, we take the bottom plane, set it to original or relative, it's unrelevant in our case, and we will set this to vector. We want to pull the position of the bottom object, which is the value, and the bottom object has the UV map. We will call it 2, UV map 2. So we want to pull with a named attribute node, set to vector. We want to pull our UV map 2. UV map 2. Our sample UV is our current UV map, which is our normal UV map 1. Now we have our position, and we take a set position node and set this as our position. Of course, we have to subdivide it, and now this works. If you set it to original, you can see, and you can of course also change something here, and it will also change on the top. Let's move on with the next node, which is the scale elements node, and let's delete everything, and we want to use a icosphere, and here we can create a cool effect. For instance, we can take our cool dual mesh node and we can create a little shield, and we can split our edges so they're not connected anymore, and then we can take our scale elements node, scale elements, and without this, you can see we can just scale our whole object or just a single axis. But if we split our edges, we can scale every single face. And with this, we can create cool effects like If we grab a noise texture and into the scale, we can make really cool effects like this, and you can play with the scale. And then you have a cool shield effect like this. So this node scales your object or the faces or the edges, whatever you want. Next node is the split edges node. So we had it currently, so this node splits all of your edges. So if you have a face here, you can see it's connected with all the other faces. If you say split, you can see it's not connected anymore. So this is what this node does. And you can of course also define a selection. So for what part you want to have this node. Very simple node. So the next two nodes is, I think most of you know those nodes. So subdivide mesh just subdivides your icosphere. So if you go into edit mode, click on subdivide, this is what it does. It doesn't change the shape of your object, but it does give you more topology. Of course, you can higher it up. Will be. And below that, we have the subdivision surface. This will smooth your object. And you can see here we have split this face. So it looks different here. And you can see this smooths your object. And we have split this edge here, so it looks weird, but let's look from here. And you have here also this edge crease. So how much it should smooth your mesh. Also vertex crease. And you can control this with a field. Very simple. I think you know this. It's as the modifier exactly the same node, maybe with more properties. Next node is the triangulate node, and this node is also very, very simple. If you use it, you can see a difference, but this is because this node takes your current faces, and if they have 4 edges, it will split your faces into 2 triangles. So it converts every face to a triangle, no matter what face it is. So if we apply our geometry nodes modifier, you can see we have a lot of triangles. Now let's move on with this category, and those are mainly output nodes, so you can grab information about your mesh. So at first we have the edge angle node, and this gives you a value for every single edge, how sharp the angle is there. So if we look from the viewer, you can see those faces here have a higher edge angle as those faces here. And if you grab a color ramp, you can see it here. If we subdivide our mesh, you can see it even more. It is like the geometry. It gives every single edge a value of the angle that it has. You can use this, for instance, if you want to have something like dirt. And the next node is the edge neighbors node. So this node outputs us the number of faces that use those edges. So if we go in here and we delete one face, we have now here 3 edges that are only used by one face. So if we use a compare and we want to compare it as this, and we want to set it to equal. So if the edge neighbors is equal to 1, like this, this outputs us a value of 1. If we now take a mesh to curve node, mesh to curve, we want to have this only converted as a curve if the edge neighbors is equal than 1. Now we only have those edges that are only used by one face. And we can join this together, join geometry like this, and we can convert our curve to a mesh. And as a profile curve, we take a circle. And now we have something like this. And every time we delete now a face, maybe also this one, we have this kind of cool pattern. This is an example you can use this node for, but let's move on. The next is the edge vertice node, and we've already used this. So this node outputs us the two vertices that one edge has. So every edge has two vertices. That makes sense, right? And it outputs us the indices for the first vertice and the second, and also the position of the first and of the second. So as already shown, if you take a vector math set to distance, you can get the length of every single edge, because this calculates you the distance between the first vertice and the second vertice. And those are connected with an edge, so you can get exactly the edge length of your edges. The next node is the face area node, and this is a very simple node because it outputs you the face area every single face has. So if we will look at it, you can see those faces are a little bit bigger than those because it's brighter. And you can get the total amount of the total face area of your whole object if you take an attribute statistics. Where is it? Attribute statistic node. And you use the face area as attribute and your object as geometry. And we will take the sum. And now we have, if we go into the spreadsheet, we have the total, if we will switch this to viewer node, we have the total amount of 6.1 Blender units. So this, of course, always uses Blender units and not centimeters and not miles. This uses Blender units. The next node is the face neighbors node. So this node outputs us the number of edges our face has. So the number of sides, and here is the number of faces that are connected to our face. After this node, we have the face set boundaries. So here I made a little something. So I have subdivided our UV sphere a bunch of times so we can see what's going on. And here I have taken a Voronoi texture and I've used the color. And then the face set boundaries outputs us the boundaries of our face sets here, as you can see here. And then you can use this as, for instance, the UV seams of the UV map, as shown here. This is a very useful node for the UV unwrapping. So you can create here, for instance, with the Voronoi texture, face sets, and then you can calculate the boundaries of those face sets with this node, and then you can use this as seams in the UV unwrapping. After this node, we have the is face planar node. This node outputs us simply if a face has the same normal than another face. The next node is the is shade smooth node, and this node just gives us a boolean of if a face is shaded smooth. So if we select a face here and we shade it smooth, then we have those data into geometry nodes now, as you can see here. A very, very simple node. And the next thing is the mesh island node, and this gives us the indice of our individual island. So an island is a part that is not connected to another part. So if we duplicate our thing here, you can see this is another island because it is not connected to the first island. And then we got another index for this island, and we have also the island count. So this is first and second. And yes, if we have more islands, then of course this gets updated. We have already used the shortest edge paths, so we will be moving on with the vertex neighbors. So this node simply gives us the number of vertices that are connected to our vertex via a mesh. This is equal to the number of connected edges. And below we have the face count. So here we have an integer for how much faces contain our vertex. And this was nearly the last node. The last node is the set position node, set shade smooth node, sorry. And this is a very cool and simple node because you can set parts of your mesh or your whole mesh as shade smooth. As in the viewport here, you can use this, and then you can toggle if something should be shaded smooth. And you can also use a random value node or another mask. Of course, you can also use something else with a boolean and into shaded smooth, and you can randomly shade your faces smooth, or you can use another mask or another input here, for instance a vertex group. And yes, this were all the nodes in the mesh submenu. Here we can delete everything and we can add back in a plane. Now we can drag our window here up and we can open the geometry nodes editor on it. Now I will close this window here by either collapsing it or pressing N, the N key. And we want to create a new geometry node tree. Now in here we can add with Shift A, or here on the top left on the add, we can add nodes via the add menu. And here we have the point menu and the instances menu, which we will go over today. Now we can start with the point menu, and here the first node I want to show you is the distribute points on faces node. We can click this and we can attach it to our noodle here. And you can see we have a bunch of points on our 3D viewport. Now, this node places points on the surface of our object, which means on every face it will distribute points, so places points. But what are points? Points are just coordinates without further mesh data, so they are just coordinates with some attached attributes, but nothing more. And in cycles they can be rendered as spheres. As you can see here, it's much quicker to render than actual geometry spheres, and you can make great particle simulations with them because it's not really mesh data you're dealing with. In here you can choose how much points you want to distribute on your plane or on your mesh. You can also change the seed, but there's a second mode for this node. So we also have the poison disk, and so the random mode just distributes points randomly over your surface, but the poison disk also distributes points randomly, but you can choose a minimum distance that every point has to be to the next point. So we can type in here the density maximum of 100 or 500, and this is exactly the same as the random, but now we can make a distance minimum of 0.1 meters. And now every point has to be a minimum distance of 0.1 meters. And we can make this density even higher, but nothing really changes besides of that they're getting more accurate. And here we have also the density factor. That is a cool mix thing. So for instance, for the density factor, you can use a noise texture like this, and maybe a color ramp to have a better control of this. Like this, and maybe make it 0.5. And of course this isn't working because we have too less geometry. So let's grab a subdivide mesh node and let's subdivide this a little bit. And now we can define it a little bit better. So this is what the density factor is for. So this is a mask you can apply that says where your points should be and where your points should not be. And as for the random, you can of course do the same in the density, but you have to higher up this to your value that you had before, so 90. So let's plug in here 90. And you have to plug in the color, of course. Now this is working properly. And as I said, these can be rendered as point clouds in our geometry nodes editor. And to change the size of those, there is an extra node in the point submenu, and it is the set point radius. You can plug it in here, and here you can change the radius of your points, and then you can change the minimum distance so they are more like this. And this is already looking pretty good. And I think we can move on with our next node, which will be the distribute points in volume node. For this we can delete everything, maybe delete everything also in the viewport, and we want to have a monkey, the Suzanne head. So with Shift A in the viewport, just add a mesh and a monkey, and we want to apply again our geometry nodes editor. Now in here we want to add our new node, the distribute points in volume node. But as you can see, it's not really working by this I message here on the top. And this means input geometry has unsupported type mesh. So this doesn't work on meshes. This only works in volume. How can we create volume? We can convert our mesh to a volume. So in the mesh, then the operations, and here is the mesh to volume node. We can plug this in here, and now you can see something is happening. So we can look on here with the viewer, Control and Shift and click. So now we can look what our steps look like on here, and you can see our monkey has been converted to a volume. Now in here you can change the voxel amount and the density. We want to have a little bit more voxels so it has better resolution. And in here you can also change the interior bandwidth and if the volume should be filled and if not. Now we have our volume, and in this volume we want to distribute points in three-dimensional space. So we use the distribute points in volume node, and now we can dial in the density, how much you want, and now you can see this is a three-dimensional cloud in the volume of our monkey. And now you can also see if I check out the fill volume, you can see it's only at the edges, which will then be nearly exactly as I would use the distribute points on faces node. So I check again fill volume, and now it's back again. Now in our distribute points in volume node we have also two modes, and the first is the random mode, which places our points randomly in the volume of our mesh. And then we have the grid mode, which places points in a grid shape and fills with that our volume. Now in here we can lower this, and with that we have more points because they have lower distance between them. And we can do this in every single axis. And with this, those two nodes should be, I think, relatively clear. And do you know what's also clear? The huge and amazing animation course from 2Animate, which you can find with the link in my description. And what can be clearer than a video that shows you what's that all about?
Hey! Ever wanted to animate something cool? Well, now's your chance. Join me and my loser brother on our adventures across the galaxy. Come shoot some bad guys.
Ride a hoverboard!
Learn to swing a sword. Whew. And become the artist you've always wanted to be.
So what are you waiting for? Think of all those animations and all those stories stuck in your head. Well, we've made 2Animate to be a one-stop package to help you bring those ideas to life, no matter your experience level. Even if you're just starting out, don't worry. We've structured the lessons to help you navigate in Blender like a professional in no time. Once you've mastered the software, you'll learn the foundational elements of animation and how to streamline your workflow using the right tools. We'll guide you through the process of creating impactful animations from scratch and cover each step from brainstorming all the way to polish and render, so that you gain a full understanding of the creative process. But moving a character is just one piece of the puzzle. How do you push your poses? How do you add texture and personality to your work? And last but not least, how do you combine it all to create a professional demo reel? In this course, you're not going to find the typical copy what I do tutorials. We'll be exploring techniques and dissecting the principles of animation so you can feel comfortable creating any type of shot in any setting. Results will come naturally from your understanding of the art and will reflect your style and your personality. Now, we know that learning a new skill and learning a new software isn't always smooth sailing, and you might run into issues along the way. That's why you'll have access to our forum, where we'll answer all your Blender related questions so you'll never get stuck. You'll also be introduced to our 2Animate community, where you'll have a chance to meet like-minded people, discuss art, show off your work, and so much more. By the end of this course, you'll learn how to develop the right mindset to succeed in the industry and have a kick-ass demo reel to back it all up. So what do you say? Are you ready to animate?
And now we can move on with the points node. And this is a very simple node, so we can look at it from the viewer. This just at default adds 1 point here in the middle, but we can make the point cloud larger, maybe a point count of 4, but you can still only see 1 point here. And this is because they have exactly the same position as you can see here, so we can change the position depending on our index, and you can of course also change the radius of them. How can we see that we have 4 points? For this we can go here in our spreadsheet, and we want to see what the viewer node sees. And here you can see we have points, 4 points, and they have all the same position. So all those 4 points are here at the center. But now we want to see our 4 points, so we have to separate them. For this we can use the index node, and the index just gives, we can look at it, the index gives for every point. So it just counts our points, as you can see here. So on our first point, we have the number 0, and on our second point, we have the number of 1, because the index always starts with our 0. So with this, we can use the combine XYZ node and use this on one of those axes, and we can use it as the position. And now we can see that we have separated our points, because every point gets another indices, and this defines how high it is going on our z-axis. Of course, we can add more points now, and they all get updated. Of course, you can change this with a math node. You can change with that the distance, so if you want to have them really close, then you can do this. And we can delete this little construction here. And now we can use our points to vertices node, and this just converts our points to vertices, which is a mesh. So this should be pretty simple. So if we now apply our geometry nodes thing here, then these would be individual vertices that we can play around with in the edit mode, like this. So let's go back, and this is a very simple node, so just converts our points to mesh data, which means vertices. We can delete that and go over to the next node, which is the points to volume node. This is also an interesting node, so if we lower here the spacing maybe to 0.3 again, we can also convert our points back to a volume. So every point gets a field of volume around it, and it looks like this. And we can take the radius maybe a little bit down so you can see something. So now every point has a field of volume around it. If we make the density higher, you can see what I mean. And yes, now we can, of course, do another thing. We can now go into the volume submenu, and we can convert our volume back to a mesh. And it looks like this then. And of course, we can update it here. So maybe 0.2. And this looks very interesting. So now in here, we take our monkey and convert it to volume. Then we place our volume grid, our point grid in this volume. Then we convert our points to a volume field. And then we convert our volume field to a mesh. Now we can delete those two. I think they are understandable. So with this, we are ready with our little point submenu in here, and we can move on with our instances menu. But what really are instances? So if we want to use here on every point an sphere like an icosphere, our render would be very slow, depending on how much points we would have. But if we would only have instances on those points, then cycles especially would be very fast, because instances only duplicate the geometry but not the mesh data. So you can see it in the viewport, but it takes one time the mesh data of our object, but then takes that one time data and only changes the position on our mesh data. So in here, in the instances, we can use the instance on points node, and we want to use for every point that we have created here, we want to use our icosphere. How can we do this? We can use the instances on points node, and here our points, we can plug them into the points, and we want to instance something, so the UV sphere should be placed for each point. And now it looks like this. Now, of course, we want to have it way smaller, so you can either take the radius from our icosphere down, or you can take the scale in our instance node down, like this. And now this is very performant even when we take the subdivision up to 6 times. And we can even make way more points. So, really weird. Blender crashed. So let's open it again. And no problem. So we can create again a Susan monkey, and we can go back into our geometry nodes editor. And now where were we? We wanted to look at our instances on points node in here. So we have to create, now we can create points on faces. It doesn't depend, we only need points. And we can also instances our monkey again. So now we take our points here on the surface and we place for every point, we place our original monkey again. Isn't this cool? So here we can lower the scale, and now this looks like you did really work, but you only had 2 points, 2 nodes, so easy peasy. Now you can use the rotation that comes out of the distribute points on faces node and plug this into the rotation. So now every monkey is rotated properly like the points would, and you can use that. And another tip is you can use the random value node for the scale, and you can take the max down to 0.1. So now every monkey has a random scale like this. It's useful for when you make grass or nature like stuff. And this is mostly what I want to show you for the instances on points node. And we can move on with the instances 2 points node. So here you can, it's a node I never used, but here you can convert your instances back to a point. So I have no idea why you would use this. It's the exact same as the output from the distribute points on faces node, but hey, you have it here. So I never used it, so let's delete it. But I've told you what it is. So now in here we have the realize instances node, and this is a really important node because if you want to use the set position node and you want to change the vertices of every single monkey in here, for instance with a noise node and a mixing of linear light, then with instances this doesn't work. This only changes the core position of our instances, because as I told you, instances don't really have access to their mesh data. It's just one-time mesh data distributed all across our scene with only changing the core position. So we can only change the core position. So we have to make out of our instances real geometry again so that we can change the individual vertices of our monkeys. For this we have the realize instances node, and we can plug it in here. And now if we use our linear light, you can see we can change the individual vertices of our meshes like this, and you can get really crazy with this like this. And yes, so this is a really important node, and yes, for turning your instances back to real geometry. Now we have also the rotate instances, scale instances, and translate instances. Those are 3 nodes which are pretty self-explanatory. So the rotate instances node, with that you can rotate the instances on their own in a local space or in an object space like this. And you also have a pivot point. So yes, it's a pretty fun node. So you can change the rotation of your instances depending on what you have. So the scale node is pretty much the same. So change the scaling on every individual monkey or as an whole object like this. And of course you have also the center here like this. And translate instances is changing the position. So with this you can change the individual position of your monkeys, or as said, as an object on its own. And yes, those are 3 nodes which are pretty simple, and I think I don't need more. And the last 2 are also pretty simple. This is a node which outputs you the rotation from your instances. I can't tell you more about this, I never used this one. And this outputs you the scaling factor of how much your instances are scaled. And yes.
The compositor is amazing. Once mastered, it allows you to do so many things that you probably could not before. Need to change the color of an object? Easy. Forgot to add depth of field? Easy. Forgot to even texture your model? Easy. I will be explaining every single compositor node. There are 87 of them in total. You don't even want to know how long this took to make. The bokeh effect is incredible. It can add a lot of mood to your scene. The bokeh image node specifies what kind of shape that your bokeh effect should be, whether that's a hexagon, a square, even a triangle. This node can change the rotation, roundness, and other effects. It's useful when used with the bokeh blur node to create the bokeh effect. The image node is used extremely commonly. With it, you can import any image type or movie file supported by Blender to implement into your scene. Images that are dragged into an empty part of the editor will be added as an image node. In this example, I use an alpha over node to drag a smoke image on top of the other image. The mask node does not create masks. You'll do that in the image editor by going to mask mode, creating a new mask, and then once you're done, going back into the compositor and selecting the mask that you just created. Once you've done this, you're free to use this mask however you want. Using an alpha over node, you could replace footage with other footage. You could add specific elements over specific parts of your image. It's really up to you how you use it. You can use either the movie clip or the image node to import footage. The difference is this. With the movie clip node, you're working with Blender movie clips. You can edit, track, and mask these in the movie clip editor. Here you will not find the footage you've added as an image node. While the image node has more options immediately available for frames and offset, you can edit these options for movie clips in the movie clip editor. The render layers node has direct access to your rendered layers from your 3D scene. Most of the time you're compositing, you'll be working with 3D layers, so you'll need to get familiar with this node. What I like to do to separate my layers is put the objects in separate collections and create new layers up with this layers tab. The RGB input node generates an RGB color value that can be shared across multiple inputs. Keep in mind that you can also drag and drop colors to copy over color data. The texture node does not itself generate textures, but instead uses textures from your texture panel. I found this is a great way to use procedural textures in the compositor, clouds or noise for example. Here I'm using it as a factor to decide which parts of the image should be affected by this purple hue. The time node outputs a value from 0 to 1 based on the progression of time from the start frame to the end frame. You can alter this output with the curve parameter. It's a little outdated due to the graph editor, but it is still cool that you can animate some sort of image fading in over this beautiful masterpiece. If you're wondering exactly what I'm creating here, by the way, so am I. The track position node provides information about specific tracking points such as the X and Y values. One example of something you could do with this is combine the speed output with a vector blur to fake motion blur. We will be getting into the vector blur node later on. It's a little more complex, so stay tuned. And finally, for the input nodes, we have the value node. It's used to generate a numerical value that can be used more than once in your node tree. The composite node is where all of your nodes connect. If you wish to see your changes reflected in the renderer, you're going to need to use the composite node. The file output node is used to output images based on the input provided in the settings in the properties panel. Something interesting about the file output node is that if you have auto render on, it will automatically save these files whenever you make changes to the input. You can make multiple file outputs from multiple stages in the input. This could mean that you could render out your passes individually just by plugging each pass into a file output and turning auto render on. The levels node reads the individual color channels of its input and outputs resulting values such as the mean or average or the standard deviation. I'll let you read up on that one if you want to. Now, there are tons of channel editing nodes available, but one unique effect that I did find is that if you separate all of the channels of an image and then combine them as RGBA with this node, you can find the average color of an image. I don't know when you use that, but it's pretty cool. You can also plug an image into the luminance level and you'll be able to see overall how light or dark an image is. That might be a little more useful. The split viewer node is like a viewer node, except it allows you to take two inputs and display two backdrop images side by side. You can use a factor slider to control between these two, and an interesting fact is that if you go into the image editor, this can actually be displayed using the viewer node option. You can choose whether to split this on the y-axis or the x-axis. And finally, the viewer node. If you shift control click on a node, it will snap itself into the active viewer node. Now, how do you set an active viewer node, you might be asking? Well, you just click on it and you'll get a red bar on it, and that'll show that it's active now. All viewer nodes are useful when something is a work in progress and you just want to preview how it's going. But keep in mind, if you want it to show up, you're going to need to check this box up here that says backdrop. And if you want to adjust the size of the preview you get, you're going to use these zoom options, move or fit, in the view panel down in the end menu. I say end menu, I mean you just press N to open it. That does it for output nodes. Let's move on to color nodes. The alpha over node overlays a foreground image in the bottom socket over a background image in the top socket. You can use this factor slider to adjust how much of an effect there is, and you may need to adjust whether the alpha channel is pre-multiplied. You can look further into the details of that if you want to, but as a rule of thumb, if you're seeing weird issues with your alpha channel, you may want to check the box that says convert pre-multiplied. This of course is useful for layering your passes and overlaying elements. The brightness/contrast node adjusts the brightness of its input in an additive fashion, while the contrast slider adjusts in a scaling fashion. But all you need to worry about is that it adjusts the brightness and contrast of its input. The color balance node is part of the color correction workflow. This node can adjust the colors and values of your images and layers. In general, you'll use the lift to adjust shadows, gamma to adjust midtones, and gain to adjust highlights. It's very useful for adjusting the mood or the feel of your scene, as just a slight color change can change everything. I like to think of the color correction node as a color balance node on steroids. It combines the essential features of gamma, gain, and lift, also adds saturation and contrast, allows you to define where your midtones start and end, and adds channel-specific corrections. The only thing you can't do is actually adjust the hue of these layers. For that, you'll need something else. The gamma node adds a gamma correction to your image or layer. Now, gamma is a complicated concept on its own. Essentially, a gamma adjustment adjusts all tonal regions but proportionately less as the tones get darker. It's meant to correct the discrepancy between how our eyes and digital sensors perceive the world, at least how I understand it. This is a very top-level description, and further research would be necessary if you want to understand the concept fully. The hue correct node adjusts hue, saturation, and value based on pre-existing hue regions. So for example, we could take this sky and make it a lot more dramatic just by adjusting the hue of these blue regions in here. We could increase the saturation of the foliage by increasing the saturation of these green and early yellow areas. And we can make these cliff faces a bit darker and out of the way if we decrease the value on these pinkish to bluish areas. Hue saturation value, on the other hand, adjusts hue saturation value not in specific regions, but on the entire image. Hue is for shifting color tones. Saturation has to do with the power or vibrance of the color, and value has to do with the brightness of the color. An interesting use case is animating these values because they have inputs with this node. The invert node takes whatever RGB input you give it and inverts it, produces a negative. You could also use this if you're looking to create some sort of inverted mask using the alpha channel instead. Anytime you need a negative or something inverted, this is your node. The mix node is called the mix RGB node back in the shader editor. Now this thing is useful for all sorts of things. There are a ton of blending modes in here used for mixing images together. Some of my favorites that I actually use a lot are hue and color from this top menu. This is ways that you can actually introduce color into a scene. All those hue nodes, all those saturation nodes, they only can work with hues that already exist. But with a color or something like this, you can introduce color. Now I know many of you already know that you can mix images and things like this, but the main purpose of this is to mix images. It's nothing like the alpha over. Instead, it's meant to actually blend images or textures or things like that. Some common ones are multiply, add, screen. You could use this to combine different masks and to create more complex masks. You could even use this to engrave invisible watermarks into your images and then also decode those watermarks if you want to. I'm serious, this is a real thing. I'll leave a link to the explanation in the PDF. The RGB curves node allows you to make color and level corrections on a channel basis. This could be combined, red channel, green channel, blue channel. Something else that is very interesting is taking advantage of this black level and white level. If you're working with an image that has some extreme color distortion like this, you can actually use this black level and select a very, very dark portion of the image. Use a white level to select a very bright portion. And you can actually bring it back nearly to its original state. And I think it's based mainly on the hue differences that still exist. It's a very cool feature, and if we actually just add in some more color correction nodes back in here, adjust the saturation, we can get this back very closely to its original state. But it's also useful for other color effects and filters, contrast correction, fixing black and white levels. It's all there. The tone map node changes the way colors are mapped in order to properly display HDR images on displays with limited dynamic range. Sometimes this happens automatically, but this is useful for managing how HDR images are displayed, particularly, again, on displays with limited dynamic range. Where the alpha over node layers elements based on alpha channel, the Z combine node layers elements based on distance from the camera. Notice how none of these layers that I'm going to show have an alpha channel that I'm using. But as you can see in the case of the sphere, it is actually layering these effects based on how far away they are from the camera. It's a very cool thing, and it's useful for various niche effects, such as combining scenes with background matte paintings. That should do it for color nodes. I'll see you back in the converter nodes. The alpha convert node converts between straight and pre-multiplied alpha channels. Again, you can do some more research if you want to understand the difference between these two things more. It has to do with the transparency is calculated, but sometimes you'll notice these little jagged edges. But if you convert from straight to pre-multiplied, you may see those just go away. Some workflows will require you to work with a straight alpha channel, which is why this exists, as a lot of the images tend to be pre-multiplied, but this is one of those things that would take longer than 20 seconds to explain. The color ramp node maps input values to a color or alpha gradient. You can then adjust how this output is displayed by adjusting these gradients. There are multiple interpolation methods. One of my favorite is constant. It allows you to create some sort of cool NPR style. I'm a big fan of NPR in case you guys don't know that. It's used to colorize images, edit texture colors, and maybe even create alpha masks. As you can see, you can also adjust the alpha values. Again, it's all up to you how you use it. Alright, I'm going to talk about the separate and combine nodes all at once because they all essentially do the same thing. They'll separate or combine images into multiple different channels based on a given color space. These color spaces include hue, saturation, value, red, green, blue, luminance, U chrominance, Y chrominance, luminance, chrominance blue, and chrominance red. They're usually used together with a separate and a combine, and then you take one of them out, and then you can edit that with like a mix or something like that. Either way, really useful nodes. You'll see these used a lot. The ID mask node is going to output an alpha mask based on the object or material index pass. The way that you set up these index passes is by selecting an object, going into the object data panel under relations, and change the pass index to something other than your other objects. It's also possible to do this with materials and make masks based on materials, which is awesome. After that, you're going to need to go into your view layer properties. First, make sure that you're in cycles, and then enable the object index and material index passes. Hit render, and then you'll be all set up. Now, if you plug in the index OB pass into the ID mask, you'll be able to select from your different index numbers, and you'll be able to select your different objects individually if you put them on different layers. This would be useful, for example, if you wanted to change the color of one of your objects in post, and you could just plug in your ID mask into the factor, and there you go. I personally believe there may be a better way to go about this sort of edit, but we'll get to that later. The math node runs various mathematical operations on its input. For example, you could add to the hue and that will adjust the tonal regions, or you could multiply the luminance and that's how you would adjust the total luminance. You're going to be using the math node for most edits that cannot be achieved with a dedicated node. Anytime there's a more complex edit happening, there's probably math nodes involved. It's worth getting to know some of these operations, but obviously you don't need to know all of them. The RGB to black and white node converts RGB input into grayscale using the luminance. It's useful anytime you need a grayscale or a scalar version of your input. So this could be used for dramatic effect or for texture purposes, anything like that. The set alpha node does exactly what it says it does. It sets the alpha value of an input. So if I make it 0.5, it's going to be exactly halfway transparent. 0, it's going to be completely gone. 1, it's going to be fine, and it doesn't go above 1. But notice how this has a scalar input, which means that this can be animated, so you could use this for a fade effect, transparency, really any alpha-related effect. The switch view node is an interesting one. It's meant to be used with this tab here in the output properties called stereoscopy. Now there are dedicated tutorials on this topic that I recommend you check out because I'll have a little bit more time to talk about this. Essentially, whenever you're in a cinema and you see that blue and red effect, that's what this is for. It uses a left and right view to produce this effect, and the switch view node combines a left and a right view to give you a single stereo 3D output, so you could make edits to individual views on here and then combine them in the switch view. The bilateral blur node blurs images while retaining sharp edges, as opposed to the blur node, which does not retain the sharp edges. The iterations on the bilateral blur controls how much blur there should be. Both of these are going to be useful for things like blurring reflections, blurring specific layers, faking depth of field, for example, reducing noise, even though there's better options for that, and a few other things. Now the blur node itself, you can adjust the effect of the blur on different axes, such as I could bring the X value up to 100 and it will blur 4 times as much on the x-axis. I'll leave it to you to experiment with all of these different filter types. I tend to use Gaussian, which is the default, so there's that. The bokeh blur node generates a bokeh blur effect using a bokeh image node with in-focus and out-of-focus regions. It's useful for faking depth of field and creating creative bokeh effects. If you check the variable size checkbox, you can actually use an input scalar to affect the size of this blur, a size of 0 being no effect. The defocus node blurs image input based on a mask or map input, including the Z depth. I found it mostly useful, again, when faking depth of field. The denoise node denoises its input images using open image denoise. It's useful for just removing noise from your scene. Here I threw at it pretty much the most noisy thing I could possibly create, and it spit out what we have on the right. Clearly you're going to want to have more samples than this, but it is an impressive display of what this node is capable of. The despeckle node denoises input images based on area complexity, so it's going to look for a lot of deviation. And so if I bring this despeckle on, here you can see that we've gotten rid of a lot of those fireflies. This threshold is what you're going to adjust, sort of find those fireflies. Ideally, you probably don't use this node by itself, but it does a pretty good job of removing fireflies if we compare these side to side. The dilate/erode node applies a mathematical shape analysis filter. It's useful for effects around edges or expanding or shrinking masks even, and other creative effects. The directional blur node blurs an input based on a blur origin. It's useful for faking motion blur or making those memes, you know what I'm talking about. So the way that you adjust this is with this center here. I can change the origin of this blur, and as you can see, it's just kind of following wherever I set it. It's actually a pretty cool effect. You can also change whether this effect actually zooms. It's all there. The filter node applies various effects and filters for creative effects, softening images, etc. Things like that. You've got soften, sharpen, laplace, that one, prewit, that one, kirsch, and shadow. The glare node applies various glare-related effects and more, such as glow effects or fog or lens flares. I've found that the fog glow is closest to a bloom effect if you're looking for something like that. There are various settings such as a threshold and a mix with the original image. The inpaint node extends image borders into masked areas. Now I don't personally have an example of this on hand, but this would be useful if you had like a small streak of transparency that you needed to get rid of. Control points, transparent holes. There's a few instances where I can see something like this happening. If you happen to run into it, just remember that the InPaint node is what you need. The Pixelate node is used to pixelate input images, although it doesn't do anything by itself. You're going to need to add a Distort Scale node, which we'll get into later, before and after. Now, on the Scale node on the left, this is where you're going to bring it to the pixelated size, if that makes sense. And then on the Scale node, you're going to bring it back to its original size. And the Pixelate node is needed in the middle, otherwise it's not going to have any effect. Now this is cool and all, and you can adjust, again, how much of an effect there is by making this value lower and these values higher. However, I feel like it would be a lot more convenient if these settings were just in the Pixelate node. The Sunbeams node is used to simulate light scattering based on image brightness. It can be used to skip volumetrics, render times, or add flavor to a bright scene. It's a little complicated to set up, but here's what we're going to do right now. Go from this image to this image. Alright, let's make this happen. So first I'm going to take this image and I'm going to separate it into UVA, which is luminance, and then U and V chrominance. I'm going to drag the luminance into a color ramp so that we can get this sort of a mask, because that's what the Sunbeams needs. It's not going to do anything without that. So we bring that in, and now it's going to use the white parts to create sunbeams. Perfect. Now I'm going to drag that into an add node with our original image, and that is going to create our sunbeam effect. However, I also wanted to cut out this bottom sunbeams and just use the top, so I created a box mask like this, and I will use that as the factor for this add node. Except it's inverted, it's just cutting out the top, so I'm going to slap an invert node on there and call it good. The vector blur node simulates motion blur using the vector speed render pass. There's definitely an art to it, but I can see how it would save some time. That does it for filter nodes. Let's move on to vector nodes. The map range node converts an input value range into a specified range. Now this is really useful if you need to clamp ranges, if you need to visualize a range such as the Z depth, except I think there's a better node for that. It's called the normalize node, and we'll get to that in a couple seconds. The map value node has sort of a similar function, but this one allows you to offset the value range as well as some other options. Now the normal node produces both a vector output and a dot product output. Now the way you're going to use this is turn on your normal pass and you'll receive something that looks like this. Now, you plug this into the bottom of the normal node, and now you've got both a normal and a dot output, and now you can basically put this into anything with a factor, such as a hue saturation value, plug that into the factor, image into the image. Look at that. So now if I bring the value down on here, we can use this normal ball here to essentially relight the scene. But this will be pretty common if you're making any edits involving vectors. The normalize node is immediately helpful for visualizing any sort of value range that goes beyond 0 and 1, such as the Z depth on render layers. As you can see, it just returns a white value, a totally white image, because the range is beyond 1 and so it will visualize as white. So if we drag this into the normalize and then visualize that, it will remap this value range from 0 to 1, and now we can actually see what's going on with this Z depth. The vector curves node maps input vector data to a curve. They can be edited on the X, Y, and Z. It can be used for a couple of things, such as adjusting the X, Y, and Z for the vector blur node. The box mask node creates a rectangular shape for use as a mask. If you select it with something else in the viewer node, it will show you a white outline of where the mask will be, and you can just put it in the viewer node if you'd like. You may need to scale it to be the same size as your image, but once you've done that, you could use it as a factor, or really anything else that you would use a mask for. The channel key node creates a mask based on differences in various color channels. You could use this to, for example, key based on the luminance, that would be the Y in either of these color spaces, or any other color space channel. I would not recommend using this as your green screen key, however, we'll get into that later. The chroma key node works based off of chrominance. You'll set the key color using an eyedropper, or whatever else you'd like. However, you can see that we're running into problems with this image, because as you can see, the newspaper is basically green, because of the reflection of the green screen. That's just a side effect sometimes. You can adjust the acceptance and the cutoff and all of those things, and you can use this for blue screens and green screens. However, I would even hold off still. There is still a node that is probably better than this. All right, now this next one is color key. Now this one works based off of a specified color. However, the difference here is this. It's only for situations where there is very, very, very little color variance. As you can see here, there is still some color variance in the background, even though it's very difficult to make out. However, it's going to cause the key to not work. What this is most useful for is honestly digital green screens. If you make a green screen in your render, for instance, or if you download some green screen footage from YouTube or the internet where they literally just put the color green in the background. In this case, since it's live footage, not gonna work since the light causes some color variance. So the next node is color spill, and I'm gonna demonstrate it with a chroma key node, although this is not the final green screen method. Essentially what it does is this. Notice how from our chroma key, we have a lot of green outline around the subject, and it's just not very good. Obviously it's not very good anyways because of the newspaper, but when we bring in the color spill, it's gonna try and decrease that effect. It's gonna get rid of the outline, and it's gonna try to get rid of the reflection. Now this next one is kind of odd out of the bunch. It's the cryptomatte node, and this is probably one of the more powerful of all of the nodes actually. If you go into your view passes, you're gonna actually have to be in cycles first, but once you go into your passes, you're gonna go down to cryptomatte and select something like object, render your scene. If you drag in your cryptomatte render layers and then your image render layer, here's what you're gonna do. Go to preview, pick, and now you're gonna choose your matte objects. So it could be this object, could be this object. Now you're gonna go to image and you can see that it has perfectly masked out those two objects that you chose. From there, you can do pretty much anything you want with it. You could go mix RGB. All right, cool. So now we've made a color adjustment. And then if we want to bring this back on top of the original image, we put it as a foreground in an alpha over node, throw this in the background as an image, and convert to pre-multiplied. It's so good. And if you want to remove things, you can go back to pick and remove those objects, and they're gone. And if you want to add more, you can go and do the same thing. Let's add one way back there. So this is extremely powerful. You could use obviously color adjustments, blur adjustments, any kind of adjustment. So the difference key removes elements based on the similarities between both input images. So let's pretend that you have a green screen with a bunny. If you were to take a picture of the green screen with no bunny, and then take a picture of the green screen with the bunny, you could input the picture with no bunny in the bottom here. Let's just pretend that's an image, and it would find the similarities, in this case it's the green screen, and get rid of that. If you add a color spill node after this, it actually does a pretty good job. However, one of these nodes is probably easier. The distance key node is actually pretty similar to the difference key. It's got a couple more options and it uses a different algorithm. The double edge mask node creates a gradient between two masks, an inner mask and an outer mask. This is useful for complex masks where you need a gradient or feather effect. Speaking of masks, the ellipse mask node creates an ellipse shape for use as a mask. You could use this for a circular or ellipse mask, as the name would suggest. Another common usage of this mask is when creating a vignette effect. And finally, the all-in-one node for keying is literally just called keying. It's the keying node. And if you select your key color, here you can see that it just gets most of the work done. It's incredible. And you may need to actually mess with this dilate and erode effect if there's any weird outlines. And you might still need a color spill, something like that. Maybe unspill some of that blue. But as far as nodes for keying goes, this is the one that I've had most success with. Now, there's still going to be some problems that you need to work out, such as the newspaper becoming slightly transparent. Obviously, that is not ideal. If you're doing heavy keying work, I would recommend checking out a dedicated tutorial on keying in Blender. I mean, that is if you're even doing this in Blender. You could do this externally. The keying screen node is very useful for footage. Essentially, it allows you to use tracking markers to specify color gradients that will be used as colors to key out. It creates something called a plate. It's very useful for removal of green screens despite maybe uneven lighting, maybe there's some off-color markers. Finally, for the matte nodes, the luminance key node. Keys based on pixel luminance. It's really useful when keying out dark backgrounds. Sometimes when you download effects, they'll have a dark background instead of some sort of green background. And you would use the luminance key to work with this. If there's a very distinguishable difference from the dark background and the element itself, you'll want to bring this high slider down. This essentially is the cutoff where any luminance above this will be 100% opaque. But that is exactly how you should be keying out dark background footage. Other things such as color key are not going to work out the way you want them to. The distort nodes are all about distorting or deforming your inputs in specific ways. The corner pin node, for example, distorts images by displacing the corners of the image. If you're planning on something like mapping an image to a screen, you're probably going to be using the plane track deform node, not the corner pin node. We'll get to that in a little bit. The crop node crops out any unwanted area of an image or clip. You'll be using these controls such as left, right, up, and down to control where this crop will occur. You could also make it relative to the size of the image instead of a set number of pixels. The displace node can be used to displace parts of an input image based on an input vector. You could use this for glitch effects, wave effects, or other distortion effects. What I'm doing here is importing a noise texture, which I've scaled using some value nodes. And then what we're doing is scaling it on the X with a displace modifier, using it as a vector by 200. And this is the effect that we get. We could, of course, increase this to something like 500, but by that point it's just getting kind of silly. Next up, we've got the flip node, which flips an input over the specified axis. It can be used for mirroring footage, finding composition errors, things like that. You can flip it over the Y, the X and a Y. As always, up to you. The lens distortion node is meant to apply distortion effects meant to mimic real lens distortion. This could be used for things such as chromatic aberration, fisheye lens, and things like that. This distortion slider right here will give you that fisheye effect. And then, of course, the dispersion will give you the chromatic aberration effect. Alright, now is where the video gets a little bit crazy, I'd say. Take a look at this composite we have here and tell me if you think this is the original render. And everything after that is just compositing. That's right. You can retexture your models after the render. Here's what you need to do to make this happen. Make sure you're in cycles, and in your render layers, make sure you have the UV enabled. Great. Now we're going to start talking about this map UV node. All right. Now plug in the UV pass into the UV. Now you're going to plug in this texture. It could be a wood texture. It could be any texture that you want into the top there. Great. We can preview what that looks like if you want to. Wow, that looks incredible. However, yeah, make sure that your scale is, you can offset, you can scale. You can do all those typical alterations. Anything that you can do to a texture, you can do to this texture. Now, next up, we're going to be adding a color mix RGB. Plug in the map UV into the bottom socket and the regular image into the top socket. I'm going to make this one overlay. And then if we view this, this is what we've got, and it's incredible. The undistortion node, or movie distortion as it is called in the menus, is meant to distort or undistort movie clips. So this could be useful for maybe blending renders and live footage to kind of match the level of distortion, motion tracking, things like that. The plane track deform node is used to add a plane tracked element to your scene using a plane track that is created in the movie clip editor. For this, I'm going to refer you to a CG Matter video. Go ahead and click this video that just pops up if you want to go check that out. It's useful for replacing screens, signs, or any other planar object. The rotate node can rotate images or footage. The scale node is a little bit more complex. It can scale the size of the output. So you can actually set this to be the render size, the screen size, but let's say that you have some sort of element like fog that is not the same size as this image, but you still want to overlay it. You can set it to absolute if you need to set it to something special. Go to your texture or image or whatever is the background, and there you can find the width and height in pixels. You can also just set it to the render size, and that'll set it to the size of your render. Stabilize 2D node stabilizes input footage according to movie clip stabilization settings. The transform node is a combination of scale, rotate, and translate nodes. It is useful for keeping a clean workspace where multiple of those nodes can be combined into one. And finally, the translate node, which is the third of nodes that is combined into the transform node. You've got the X and Y values in here, which allow you to transform your elements on a pixel basis. And while we're at it, I think I might as well explain some of these layout nodes. The first of these is frame. You could call this whatever you want by adding something in the label here. You can drag out these corners yourself, or if you just want it to automatically happen, you can grab 2 nodes, drop it in, or 1 node, it doesn't really matter. Any group of nodes you can drop in, and it will snap to that size. Speaking of organization, we've got a reroute node. This is like a subdivision of a node noodle. You just drag and drop it in, and you can reroute your node noodles all over the place. And finally, the switch node. It takes 2 inputs and outputs either one of them based on whether this switch checkbox is checked. You could use this to compare between results, or if you want to bypass node groups for certain sequences, seeing as this switch can be animated by right-clicking or pressing the I key.
I'm an engineer in electronics, so I'm very comfortable around math and numbers, and in this video I'm going to explain each operation of the math node in the geometry node. Since Blender doesn't really have an easy way to visualize node outputs, except doing this, I'll use this grid, and the red sphere will visually represent the result of the operation, and where it applies, I'll use a blue and aqua spheres as the inputs of the operation. The math node has a clamp checkbox, which clamps the result to values that go from 0 to 1. If checked, any number above 1 will return 1, and any number below 0 will return 0, and this applies to all of the operations in the node. Functions. Here we have the basic day-to-day operations, and a section with a little bit more complex ones. Add returns the sum of the two values, so 3 plus 5 equals 8. Subtract subtracts the second value from the first one, 5 minus 8 equals minus 3. Multiply multiplies the values, 3 times 5 equals 15. Divide divides the first value by the second one, 15 divided by 3 equals 5. Multiply add multiplies the value times the multiplier and then adds the addend. So 4 times 2 is 8 plus 7 equals 15. Power elevates the base to the power of exponent. So 2 to the power of 4 equals 16. Logarithm returns the exponent or power to which you would need to elevate the base to result in value. So 2 to the power of what would result in 8, and the answer is 3. Square root calculates the number which multiplied by itself would result in value. So to get 9, you would need to multiply 3 by itself. Inverse square root calculates the square root and then divides 1 by that number. So the square root of 4 would be 2, and 1 divided by 2 would be 0.5. Absolute returns the magnitude of the number, so it removes the sign. Minus 5 will return 5, but 5 will also return 5. Exponent elevates the constant e, also called Euler's number, which is approximately 2.718, to the power of value. So 0 will return in 1, as any number elevated to the power of 0 equals 1. 1 will return the value e, 2 will return e squared, and so on and so forth. Comparison. These functions are of course used to compare numbers. For these I will also show the inputs in the chart so that it's easier to see. Minimum returns the smaller of the two values. Maximum returns the larger of the two values. Less than is a Boolean operation. These operations can only tell you if something is true, represented by a 1, or false, represented by a 0. Is the value less than the threshold? In this case, it's not, so it returns a 0. When the value becomes smaller, then it will return a 1, or true. Greater than is the opposite and will return 1 when the value is greater than the threshold. Sign returns minus 1 if the number is negative, and returns plus 1 if the number is positive. Compare is a Boolean and it returns true if the two values are within epsilon units of each other. So if I fix epsilon in 3 and one of the values in minus 6, then the operation will return true whenever the second value is between minus 3 and minus 9. If I go outside that range in any direction, it will return false. Smooth minimum I never saw before Blender, but it returns a smooth approximation to the smallest value, with the distance being the smoothing range. Let's set one value at 0. If the other value is equal or larger than the distance, then the output is exactly 0. As soon as I get within the distance value, the output is now some number but not 0, and that smoothing effect will continue until the smaller number is at least distance units from the other one. This is how that smoothing effect looks. Smooth maximum will do the same thing but towards the largest number. Rounding functions. For these I will chart the input with the blue sphere and the output as always with the red one. Round rounds up to the next integer if the decimals are at least 0.5 and rounds down otherwise. Floor always rounds down to the next integer. Seal or ceiling always rounds up to the next integer. Truncate removes the decimals of the number, leaving only the integer part. Fraction does the opposite, leaving only the decimals. Modulo returns the remainder of the division. For example, 11 divided by 3 can also be written as 3 2/3. This is a modulo. You can also input fractional numbers. For example, 9.5 modulo 3.5 could be something like 2 and 2.5 3.5. So the modulo would be 2.5. Wrap will wrap the value around the range provided by max and min. So if the value is within that range, the operation will return that value. As soon as the value goes out of that range, the result will wrap around. Now, if the value equals max, it wraps, which I think might be a bug. Snap rounds down or snaps down to the next multiple of increment. Ping pong is similar to wrap, except it reverses the direction every time it reaches a multiple of scale. scale, so it goes back and forth. On to the trigonometric functions. For these, I will chart the input value in x and the result of the operation in z. Sine returns the sine of the value. It's important to mention that the value should be given in radians, not in degrees, where 360 degrees equals 2 pi radians. Also note that you can directly type pi or tau and Blender will recognize them, where tau is 2 pi. Cosine returns the cosine of the value. Tangent returns the tangent of the value. Note that the tangent is equal to the sine divided by the cosine of the value, so when the cosine of that value will be 0, the result will be infinity. The inverse functions do the opposite. They return the angle in radians for a given value within a range. So an easy way to understand this is if I connect an inverse function to the regular function. As long as the input is within a valid range, in this case is -1 to +1, then the input will be the exact same number as the output, because the arc sine converts it backwards. It also has to be within this -1 to +1 range, as going outside of that range will clamp the result. The reason why we need to stay within the range is that we are essentially rotating the wave graph, so we can only really operate within this range. Arc cosine works in the same way, and the same thing with arc tangent, except that the input range in this one is infinite and the output will approach to -pi/2 or +pi/2. Arctan 2 is almost the same, except that it divides the value by the second value before calculating the arc tangent, essentially stretching the shape horizontally. Now the difference between the regular trigonometric functions and the hyperbolic ones is that the regular are defined by a circle, while the hyperbolic ones are defined by a hyperbola. This sounds complex, but we can easily visualize this by plugging the sine of a value to the horizontal dimension and the cosine to the vertical, and as we change the value, a circle is formed. But if we use their hyperbolic counterparts, then a hyperbola shape is formed. And finally, the conversion functions convert degrees to radians and vice versa, so as we saw before, 360 degrees equals 2 pi radians, and pi fourths equals 45 degrees. We're going to explain each operation in the vector math node and visually show it in this setup. This will be our main window, and these are orthographic views, xy, yz, and zx. This way you can easily see the exact values of each operation. The grid shows increments of 1, 5, and 10. The result of the operation will always be shown in red, while the inputs will be blue, aqua, and purple. I'll also try whenever possible to stay in the first octant, where all the values are positive to keep it simple. Now, a few things to know beforehand so that we're all on the same page.
The sum of the square roots of any two sides of an isosceles triangle is equal to the square root of the remaining side.
So what's a vector? A vector is just a collection of 3 numbers that provide information, usually a location or a rotation in a 3D space. We represent vectors by drawing a line from the origin to the coordinates specified in the vector, always in XYZ format. Note that the origin of the vector does not necessarily have to be the world origin, and for certain applications, we'll move some of the vectors around. Vectors contain 2 important pieces of information: the magnitude, which is how long the vector is, and it's always a positive number, and the direction. An example you remember from your physics class is that speed is a value that we call scalar, meaning it does not specify the direction, while velocity is vectorial, so it provides a magnitude, how fast the object is moving, and also the direction that the object is moving towards. Also note that in Blender, connectors are blue if they receive or output vectors, and they are gray if they receive or output floats. So we could say blue is vectorial and gray is scalar. And finally, we'll call the inputs A and B if there's no specific label. Now let's get into the node. Add adds up both vectors by adding each of the corresponding dimensions, so x plus x, y plus y, z plus z. You can think of this operation as putting one of the vectors at the end of the other one. Subtract does the opposite. This would be like putting the end of B at the end of A. Or you could say you're adding the negative vector. Multiply multiplies the values of each corresponding dimension. You can see this in the orthographic views. So 2 times 3 equals 6, 3 times 5 equals 15, and 4 times 5 equals 20. In the same way, divides the values by each corresponding dimension, A divided by B. And just to show one example, 10 divided by 5 equals 2. Multiply add multiplies the vector times the multiplier in the way we saw before, and then adds the addend. We can see that 2 times 4 equals 8, plus 1 equals 9, which we can see here, and 3 times 2 equals 6, plus 2 equals 8. We can see in the y direction it's an 8. Cross product outputs a vector that is perpendicular to both input vectors, with the magnitude being equal to, and bear with me for a second, the area of the parallelogram formed by both vectors. This will be crystal clear in a second. So if these two vectors formed a plane, then the result will be perpendicular to that plane. This is easier to see when both inputs are on one of these planes. If we zero z on both inputs, now both of the input vectors are sitting on the green plane, and that means that the cross product should go directly up or down, since those are the two vectors that would be perpendicular to this green plane. And you might be wondering, then how do we know what direction the result will be, since both vectors, positive or negative, would be perpendicular to both inputs? Engineers use something that's called the right-hand rule. You put your fingers like this, with the index pointing towards the A vector, here the blue one, and the middle finger towards the second vector, here it is the aqua. The thumb will point towards the direction of the cross product, and we can see that it in fact goes in that way. And now for the magnitude, it's this area. We say parallelogram as the shape might be a square, a rectangle, a rhomboid, or a rhombus. And so the term parallelogram encompasses all of those shapes. That's why we use that fancy word. Now, if both vectors point exactly towards the same direction or away from each other, then you'll see that the magnitude is 0 because there is no area in this shape, as it's just a line. But as soon as we break that line, we can see that the magnitude changes, as there is now some area in this parallelogram. Project projects the A vector onto the B vector. The resulting vector will fall along an infinite line defined by the direction of B. You'll see that the resulting vector is not bound by the length of B, so it can go beyond B in either direction, but it will always fall on the axis created by that vector. Reflect reflects the vector A around the normal B. So if B is a normal, then we can create a plane that has that normal. Then the result is the reflection of A around this plane that is defined by the normal B. You can also understand this as A being the incident vector, and then the result is the vector that will be reflected on this plane. Refract refracts the vector A around the normal B, considering the index of refraction. You can see that there's a slightly different angle between the incident vector and the result based on the index of refraction. And in the same way as before, you can think about the A vector as the incident vector and the result as the refracted ray around this plane. Phase forward is kind of a mess how this is written, but this is how I understand it. Exactly. So if we take the reference as the normal of a plane and we add this plane, we can see what's happening. So what it actually does is it returns the input vector whenever the incident is pointing towards the opposite side of the plane than the reference, and returns the negative of the input vector whenever the incident is pointing towards the same side of the plane than the reference. So as soon as the incident crosses the plane, then the operation will just return the input vector. You cannot see it here because it's on the same place, but if I move the input a little bit, you'll see that it's there. Dot product does not return a vector, it just returns a float number equal to multiplying the magnitude of A times the magnitude of B times the cosine of the angle between them. In this cosine chart, you'll see that if the angle is higher than 90 and lower than 270 degrees, then the result is negative. If it's exactly 90 or 270, the result is 0, and otherwise it is positive. So back in Blender, we can see that the result is positive as long as both vectors remain within 90 degrees of each other in any direction. But as soon as we break those 90 degrees, then the result becomes negative. If this sounds familiar to Phase Forward, it's because they use the exact same math. Distance also returns a float equal to the distance between both vectors. Length returns a float equal to the length or the magnitude of the vector. Note that the magnitude has no sign, so it will always be a positive number. Scale multiplies the magnitude of vector times scale while keeping the direction equal. Normalize returns a vector with the same direction, but always with a magnitude of 1. Absolute returns a vector with all positive dimensions, so whatever the input, the output will always fall in the first octant. Minimum returns a vector with with each dimension being the minimum between the two vectors. So x will be the minimum of both, z will be the minimum of both, and y will be the minimum of both. Maximum does the opposite and returns a vector that has each dimension being the maximum between both vectors. Floor rounds down each dimension towards the next integer. Ceil rounds up each dimension of the vector towards the next integer. Fraction removes the integer part of each dimension, leaving only the fraction part. Modulo returns a vector with a modulo operation of each dimension. Here's an excerpt from the math video about the modulo operation. Modulo returns the remainder of the division. For example, 11 divided by 3 can also be written as 3 2/3. This is a modulo. You can also input fractional numbers. For example, 9.5 modulo 3.5 could be something like 2 and 2.5 3.5. So the modulo would be 2.5. Wrap will wrap each dimension around the minimum and maximum vectors. Snap rounds down each dimension to the next multiple defined by increment. Sine returns a vector with each dimension being the sine of the corresponding input dimension. Note that it will take these as radians and not as degrees. Cosine is the same but with the cosine, and tangent is also the same but with the tangent.